Hello, my name is Michalis Papakostas and I would like to thank you for your interest in a research titled Understanding Driver Distractions and Multimodal Analysis on Distraction Characterization. Our motivation for this work stems from the fact that every year road accidents have a major societal and financial impact around the world, with more than 1 million lives being lost annually on the roads and several billion dollars being spent on road-related accidents. A huge number out of all those accidents are directly related to distracted driving. So according to the National Highway Traffic Safety Administration, distracted driving is described as any activity that can divert drivers' attention from the task of driving, and that can include talking or texting on the phone, eating or drinking while driving, talking to other people on the vehicle, just a wandering mind, or fiddling with the stereo, the entertainment system, or the navigation system, or any kind of activity that can affect drivers' attention. Um, so the scope of our research is first of all to create a novel multimodal dataset that we can eventually use to evaluate the intersection between distraction and drowsiness. We are interested in identifying features and modalities that are informative towards monitoring drivers' behavior and eventually building personalized multimodal driver models. So to address the aforementioned goals, we designed a multimodal dataset of 45 male and female participants between the ages of 20 to 33 years old. Its subject participated in two recordings, one that took place early in the morning and one that happened later in the afternoon. Each recording lasted about an hour and consisted of three different recording sections. Section 1 was the baseline, where we recorded sample data from the participants while they were relaxing and sitting without being engaged in the driving task. Second section was the free driving part, where the participants were asked to drive freely in the virtual environment. And the last section was the distractors section, where the participants were asked to engage in different types of distractors while driving. In particular, there were four types of distractors. First was texting, which can be considered as a physical distractor. Then it was the NBAC test, which can be considered as a neutral cognitive distractor. Neutral stands for not having an emotional stimuli. Then it was the radio distractor, where the subjects were asked to listen and comment on an emotionally intense radio recording while driving, which was also mostly a cognitive distractor, but now with some kind of emotional stimuli. And lastly, it was the GPS distractor, where the subjects had to interact with a faulty GPS that kept providing invalid feedback, thus causing frustration, stress, and anxiety to the driver. And that can also be considered as a cognitive distractor with some kind of affective stimuli, but different to the emotional one, to the radio one. And here you can see the experimental setup, where we, as I said, totally recorded 12 different modalities. And those are closer views of the sensors themselves and the output data that each of those devices captured. So for the purposes for this work in particular, we performed experiments focusing only on the visual signals and the four physiological markers that we captured, namely the blood volume pulse signal, the skin conductance signal, the respiration, and the temperature signals. And we're interested in answering the following 5 questions. Can we discriminate between distracted and non-distracted driving? Can we discriminate between physical or a cognitive distractor? Is it possible to tell exactly what kind of distractor the participant was engaged in? And finally, which is the most informative signal, and what modality-specific features are the most descriptive towards describing the different driving behaviors? So for analyzing the visual modality, we worked using what is called action unit features. And action units are the core components of FACS, that stands for Facial Action Coding System, which is a framework designed to group facial movement. And action units are used to code complex facial expressions. For the physiological features, we extracted the vast majority of our features from the blood volume pulse signal, following related research. While for the rest of the remaining 3 signals, we extracted 7 statistical features from each of those, mostly related to their temporal behavior and characteristics. And a detailed list of all the features used can be seen here. Um, so for our evaluation, we performed a leave one subject out type of evaluation, and we followed three different modeling schemes. A user-independent scheme that led to average performance scores, where all data from 44 users were used for training, and the data from the remaining user were used for testing. A user-dependent scheme which led to the best results, where all data from 44 users plus one of the recordings from the 45th user were used for training, and the remaining data from the 45th user were used for testing. And a user-exclusive scheme that led to the worst results, where for each user we trained the model using data from one of their recording session as training data, and the data from the remaining recording session of the same user were used for testing. So here we're going to talk only about the best results, which came from the user-dependent scheme, as I said. And you can find more details in our paper. On the left, the confusion matrices correspond always to the visual modalities, while the confusion matrices on the right of each color correspond to the physiological modality. So as you can see on the distraction detection problem, which is on the top left here, physiological modality was much more capable in identifying distracted driving. And we believe that this was due to the fact that most of our distractors were of non-physical nature, and visual modality couldn't capture that. On the top right, we observed that the two signals performed very similar on discriminating between physical and cognitive distractors, while on the confusion matrix on the bottom, we can see that overall the physiological markers were superior on discriminating between the four different distractors. Specifically, the visual modality struggled much more on capturing the differences between cognitive distractors, which are those three, where the physiological signals perform much better. And here you can see the results when combining the two modalities for 2 out of the 3 targeted classification tasks. In particular, on the left, we can see the multimodal results on discriminating between physical and cognitive distractors, while on the right are the multimodal results on distraction identification. In the former case, we can observe that the multimodal results are significantly superior against both unimodal approaches, while in the latter case, on the table on the right, we can make the same observation as classification recall increased almost in all the targeted cases, here in the diagonal. So next we see how present were the action units on each of the 4 distractors, or in other words, how active a specific action unit was when the participant was involved in a specific distractor. As you can tell, specific action units were very informative towards identifying some of the distractors, and in particular action unit 4, 14, or 45 were highly associated with texting, while action units 6 and 7, for example, were mostly present on the cognitive distractors. In order, though, to identify which of all the features that we used were most informative towards tackling all the discussed classification tasks, we trained a random forest classifier using all the available data we had for each of the tasks. And eventually, we computed the total information gain for each of the unimodal features as a sum of the information gain achieved in each individual task. Then, we selected the top 5 performing features from each modality, and we repeated the exact same experiments. And here you can see the features in more detail. And what is interesting is that for the visual modalities, we can see that most informative action units are not necessarily the ones that were mostly associated with a specific distractor. While for the physiological modality, it's interesting to see that all the features are related to the blood volume pulse signal and its temporal or spectral properties. And here are the results using only the top 5 performing features. And we can see that the largest differences can be observed in the visual modality in both problems of distraction characterization, which is here for the physical versus mental, and here for the distraction identification task. But other than that, in all the other cases, the results are relatively close with the original scores, with the main difference between the two experiments being that we got rid of 12 visual and 72 physiological features. So the main takeaways of our work is that we proposed a novel multimodal dataset that consists of 45 subjects and 12 information signals. We practically observed that physiological signals are much stronger indicators of non-visually observable distractors. We saw also that combining visual and physiological features almost all the time led to superior performance and created more robust models. We also showed that the vast majority of our model success must be accounted to a very small amount of visual and physiological features, especially in the physiological case, mostly related to the blood volume pulse signal. And lastly, based on the different tested evaluation schemes, we can tell that combining both user-specific and user-generic data can lead to the best possible results in similar tasks. So thank you again for your interest in our work. I do encourage you to take a closer look to our paper for more details, and please feel free to reach out if you have any questions or further interest in our work. Thank you.